Hello everybody, and welcome to example 3 on page 38 of the workbook. This is another example of just working with linear transformations, and you'll find this to be similar to the example that we did in example 1. Okay, let's read this together. So suppose that t from R2 to R2 is linear, and that t of 1, 1 equals 0, 0, and t of 0, 1 equals 1, 5. They'd like us to find a formula for t. Okay, so again, what this is saying is that if they give us just 2 points, they're telling us what happens if we substitute in 2 input values. That's supposedly enough information to figure out the formula for the entire transformation. Okay, and so we're going to approach this in the same way that we did example 1, in the sense that these 2 input vectors, 1, 1, and 0, 1, they actually form a basis for R2. We can write any vector in R2 as a linear combination of 1, 1, and 0, 1. And that's going to be the start of our work here. Okay, so let's do a little scratch work and ask the question, how could we write an arbitrary vector AB in R2 as a linear combination of 1, 1, and 0, 1? Okay, well, that's like asking, what would we need to put in the blanks so that this is a true statement? Okay, and we're going to do this coordinate by coordinate. Okay, so let's focus first on the first coordinate, A. Okay, so to get an A in that first coordinate, we want to focus on these 2 first coordinates, the 1 and the 0, in our 2 ordered pairs, and ask what numbers would need to go in the blank. Well, the first thing you might notice is that there's a 0 over here, so totally irrelevant what goes in this blank. Okay, because it's just going to get multiplied by 0. What that means is that we need to put an A here so that A times 1 gives us the A that we have over here on the left-hand side. Okay, so A has to go in the first blank to make this work. All right, let's clear away a little clutter here. And now we're ready to ask, how do we get a B in the second blank? Okay, well now we're focusing on these 2 second coordinates. Notice that we've already got an A in the first blank. We can't change that. And so we're going to get A times 1, which gives us an A. And the question then is, what do we need to put over here so that we take that A and add it to something and we get the B that's sitting there? If you think about it a minute, what we need is a B minus A. Okay, because A plus B minus A gives us the B that we have over here. Okay, now this process is a little strange the first time that you see it. Okay, so I'm going to clear away some clutter here. Let's go a couple more steps just to check this, reassure ourselves that this is really a true statement. So if we do the arithmetic with the way that we filled in the blanks, notice what happens here. We get AA for the first coordinate, and then 0 and B minus A for the second ordered pair. Okay, if we continue that calculation, we're going to get, let me go to the next line here just so this doesn't get too cramped. It's going to be A plus 0 and A plus B minus A. And notice if you do the simplification, that gives us the AB that we started with. That kind of confirms that this is a true statement. Okay, and actually, just to be notationally accurate, I should maybe put a question mark there, since at that point we didn't know that that was a true statement. We kind of checked it over here. All right, so what can we do with that? We did a lot of work just to write AB as a linear combination of these 2 vectors. Now, let's start the problem. They'd like a formula for T of AB. Okay, so we'll just make the observation that since AB is equal to A times 1, 1 plus B minus A times 0, 1. That's what we just verified above. We have T of AB equals T of that entire right-hand side and now we use the fact that we're assuming that this is a linear transformation, so we can do exactly what we did in example 1, and we can pull this apart. So this is equivalent to T of A times 1, 1 plus T of B minus A times 0, 1. There we're using the fact that T preserves addition, and then we can pull the scalars out. Okay, so A times T of 1, 1 plus b minus a times t of 0, 1. There we're using the fact that t preserves scalar multiplication, so I'm just going to leave a note here and mention that those two steps just use the fact that we know that t is linear. Okay, and then finally, we've gotten it down to a point where we've got t of 1, 1 and t of 0, 1. Those were the 2 points that they gave us in the problem. T of 1, 1 is 0, 0, and t of 0, 1 is 1, 5. Okay, so we can go ahead and fill those in. Okay, so let's see. T of 1, 1 is 0, 0. Okay, and t of 0, 1 is 1, 5. All right, and then finally, a times 0, 0 is 0. That goes away. And if we just multiply the b minus a through, here's what we get. B minus a and 5b minus 5a. Okay, and there's our formula. So t of ab equals b minus a, 5b minus 5a. That's our answer to the question.